Good morning to everyone. I'm Giuseppe Silano, a tenured researcher at Ricerca sul Sistema Energetico and associate researcher at the Czech Technical University in Prague. Today, I'm going to present the work entitled A Nonlinear Model Predictive Control Strategy for Autonomous Racing of Scaled Vehicles. The research activity is the result of a joint collaboration between the University of Sogno in Benevento, the Ricerca sul Sistema Energetico, the Czech Technical University in Prague, and the University of Catalonia. The research was partially supported by the European Horizon Project Aerial Core and Excel joint undertaking project Comfort Drones. Over the last years, the need to provide more affordable mobility and to reduce greenhouse gases from needless idling, the interest in increasing safety and productivity by reducing road congestion is creating a high connected infrastructure that is a perfect enabler for autonomous vehicles. What is making all of this possible is a set of instrumental technology that are just now reaching maturity. On top of that, autonomous driving is gaining momentum as evidenced by the numerous applications in commercial vehicles where these automatisms have proved effective. On the right side of this slide, we can see some of the autonomous vehicles that are now driving our roads in our cities. The aim is to push the limits towards the development of new technology, and one way to do that is represented by the numerous international competition on autonomous racing cars organized and held in major international conferences. Above all the competition, the F110 autonomous racing competition is one of the most popular, whose name derives from the use of 1 to 10 scaled-down car models. Depending on the task objective, the problem is faced with different level of details and approximation. In any case, each time the goal remains almost the same: do not crash, minimize lap time, and overtake all opponents. Several approaches have been proposed in the various editions of the competition. However, when vehicle nonlinearity are excited, the control task is more demanding, and this opens new challenges to be solved. The model predictive control approach has proven to be a promising solution to control the car motion. Specifically, nonlinear model predictive control has resulted particularly suitable to control autonomous racing cars when their agility is essential for the particular application and must be exploited at the best. The problem requires the car to race along the track, minimizing lap time, remaining within track boundaries, and safely compete, avoiding static obstacles populating the track. A nonlinear model predictive control architecture for line center line tracking for autonomous racing competition is proposed in this paper. Considering the case of 1 to 10 scale racing cars. The optimization problem, as I said, consider both the vehicle dynamics constraints and the physical actuation limits. Also, the car dynamics is described by bicycle model, and longitudinal and lateral forces acting on the vehicle are modeled by drivetrain model and the Pacejka magics formula. The identification process is set up to obtain the model parameters using the experimental data collected in the 1/10 simulator. The nonlinear model predictive control approach is embedded in ROS and coded using the open framework and the PANOC as solver. Both the optimal racing trajectory and the tracking lane problems are solved within the same optimization framework. The prediction model is a key part in NMPC laws. One of the most common approaches using vehicle dynamics application is to simplify the vehicle's model to that of two-wheeled bicycle model. This approximation is sufficient to provide the necessary inputs to the actuators due to the small size of the vehicle. Using the second Newton's law and analyzing the forces and the momenta acting on the vehicles, we can derive the set of equations that describe the system dynamics. For the sake of brevity of this presentation, I couldn't include all the steps and derivations. Further details are available in the paper. However, we can take a look at the equations that are reported in the right side of the slides. And this set of equations requires a few comments. First, for ease of modeling, the longitudinal forces are described by the Fx. Second, control inputs are delta, that is the deflecting of the front wheel, and D, that is the pulse with modulation signal that is sent to the motor. The end result is a nonlinear dynamic system whose state is X in R12 and R6, sorry, and the control inputs U in R2. In order to exploit the prediction model, is pivotal to identify the model's parameter, in other words, those describing the lateral and longitudinal forces modeled by the simplified Pacejka-Smegji formula, and the drivetrain model. Acceleration and acceleration experiments in the F110 simulator can be used for the identification process based on a least square minimization approach. Here we can see the minimization problem, where the x at the y and at omega represent the one-step prediction linear and angular velocity based on the discretized vehicles model, while bar zeta and underline zeta denote the range of minimum and maximum admissible values, respectively, for the parameter zeta. In the figures reported at the bottom of this slide, we can see a comparison between the identified values, so the at symbols, and the collected linear and angular velocity values. The optimization problem was coded using MATLAB, and in particular the FMINCON of the MathWorks optimization toolbox. Now, let's go to the control architecture. Let's focus on the control architecture. A two-layer control architecture has been proposed to cope with the racing problem. A reference generator algorithm provides the reference point coordinates to an NPC tracking controller, which computes the control signal to reach the point while satisfying all constraints. The reference generator supplies reference point at each instance of the optimal problem. The planner leverages the capability of computing the projection of the car position along the lane center line, and this is in line with the competition rules, and for ease of experimentation, the proposed solution assumes to know the shape of the track and therefore the lane center line. At each control step, the reference generator projects the car position onto the center line. Afterwards, the planner computes the reference point coordinates, looking at P waypoint along the lane center lines. These figures that are reported in the corner left corner, sorry, of this this slide represent the two steps of the reference generator. And the first, we can see the projection of the car position on the line center line. Instead, in the second, we can see the P waypoints look at head to determine, to obtain the reference point for the tracking controller. Now, the car is also required to avoid obstacles along the track. The collision avoidance constraint is formulated through position of the vehicle P and the JTH obstacle PJO. In the figure, we can see the collision fee trajectory that is depicted in purple, and the computed NMPC tracking computed by the NMPC tracking controller, and the static obstacle avoidance obstacle that is represented in brown. A threshold value gamma is defined accounting for the obstacle size and the vehicle's body, and to ensure a sufficient room margin for maneuvers. Track boundaries constraints are also embedded into the problem formulation to maintain the vehicle within the limited width track. The constraint is formulated considering the Euclidean distance between the vehicle's position and its projection on the boundaries. Two variables are considered in this case, RG and RC, in order to impose the constraint. The first models the track with the second the car dimension. In both constraints, the square terms ensure differentiability everywhere, while guarantee the same constraints characteristics. Now, let's focus on the optimal control problem. The optimal control problem has a prediction horizon of n steps with a sampling time t with s of 33 milliseconds. It's set up as a minimization problem of a cost function. The cost function, the objective function, as Q1 and Q2 being the diagonal weighting matrices, Pn and Pd that represent the vehicle position at the n step of the optimization problem, and the reference point coordinates respectively. 1b and 1c initialize the control input and the system state respectively. 1d describe the discretized dynamic model for the vehicle. 1e and 1f are the obstacle avoidance and track boundaries constraints respectively, and finally 1g and 1h set the control inputs and state limits respectively. Now, the control problem was coded using a single shooting implementation with track boundaries and obstacle avoidance constraints treated using the argument Lagrangian and the penalty method approaches respectively. Now, the problem has been set up and we can analyze the numerical result. To demonstrate the validity of the proposed control strategy, numerical simulation in the F110 simulator were performed. The nonlinear model predictive control strategy was coded using the open framework and Pacejka solver. Let me play the video in the meantime, describing a bit how the numerical results have been obtained and how this scenario were chosen. Let me also say that the code has been released as open source and available on GitHub. So, in the meantime, the simulation are running 3 different tracks in which the vehicle run in counterclockwise direction were considered. In all simulated scenario, the car's velocity touches the actuation limits for the most of the track. Minimum velocity values can be seen in most demanding stretches where the minimum values is just under 3 meters per second. It can be seen how the car slowed down in the sharper turns and accelerate at the exit of the turns. The same simulation were performed considering the static obstacles along the track. As you can see from the video, in both cases, the algorithm was able to control the car, staying within the boundary and avoiding collision. Now let's finish this video, and we will jump to the other numerical results. So now we can see in this figure the histogram of the computation time per control step of the nonlinear model predictive control strategy. Low computation time per control step is also showcased when considering static obstacles along the track. Hence, these graph show the capability of the proposed framework to compute the necessary control action to drive the vehicle, pushing the limits without violating the constraints. What does it mean this? This means that the control problem is able to find a solution for the SO, provide the next control input U before the sampling time, that in this case is represented with the red bar, and this is fixed to 33 milliseconds. Now, to conclude, this paper has presented a nonlinear model predictive control strategy for autonomous racing of scale vehicles. Simulation performed in the F110 simulator demonstrated the validity of the control strategy in a scenario as faithful as possible to real-world conditions. Future works are in the direction of including advanced planning solutions to deal with uncertainties on the lane center line. Also, we plan to investigate more challenging scenarios, such as the combination of static and dynamic obstacles in the direction of field experiments. Let me also thank again the 2 projects that supported this research activity. The first is the European Union Horizon 2020 Research Innovation Program IREL-CORE. The second is the joint undertaking program Comfort Zones. Thank you for your attention.